Okay, welcome class. We were discussing cache memories in the previous lecture. Let's continue from where we left. We were discussing this flowchart. Just let me go through this flowchart once again. This flowchart essentially tells you the entire process of reading the data from a system which has both memory as well as main memory as well as the cache memory. The process begins over here. As I told you earlier, the CPU always generates the address for the larger memory, which in this case is the main memory. So the processor will generate or output the memory address A, which refers to a location in the main memory. Then first of all, the CPU is going to check for this piece of information or for this address in the cache memory. As we already discussed, that the number of words in the cache memory or number of lines in the cache memory is definitely less than the number of blocks in the main memory. So the main memory address is going to be larger as compared to the cache memory address. So our first process or first issue, design issue, is to find the main memory block address B that contains this address A, which is required by the CPU. Then using the mapping function, we map this to a particular cache line and check whether this block is present in the cache or not. Now once again, there can be two possibilities, a miss or a hit. If it is a hit, then the data is read from the cache and it is given to the CPU. And if it is a miss, then the data has to be brought in from the main memory. Now once again, before we can bring the data from the main memory, we have to decide upon the cache line into which this data will be brought in. As we discussed earlier, the main memory is divided into blocks, cache memory is divided into lines. The size of a block is equal to size of a line. So one block of main memory is brought into a line. Now once again, there are two possibilities, that a particular line where I want to bring the block of memory may be empty or it may be full. If it is empty, then there is no problem. I can simply copy the data from the main memory to the cache memory and then subsequently bring the data to the CPU. But if it is full, we have to use some sort of a block replacement policy to make the particular cache line free, and then I copy the data onto that cache line. Now let us see the various possibilities of cache operation. Now cache performance, if I talk about, once again, if you see over here, there are two basic operations. One is the cache read operation, one is the cache write operation. Cache read operation means reading the data from the cache memory. Cache write operation means writing the data onto the cache memory. Once again, if I talk about cache read, there are two possibilities. This is the cache hit possibility where the data is present in the cache. This is the cache miss possibility where the data is not present in the cache. If the data is present in the cache, it is simply forwarded to the CPU. If the data is not present in the cache, then again there are two possibilities. See, I am bringing the data from the memory, but now there are two possibilities. First is I can bring the data from the main memory into the cache memory, and then subsequently I can send the data from the cache memory to the CPU. What it means is I will bring one complete block of data from the main memory, store it into a cache line, and then take the particular address which the CPU requires from the cache memory, and I will send the data to the CPU. This is this particular option. Second option can be, while I am bringing the data from the memory, I can simultaneously populate the cache line and send the data to the CPU. So these are the two possibilities. When I talk about a write operation means I want to update a particular piece of data that is present in the that might be present in the cache memory. Once again, there will be two possibilities, hit and miss. Now suppose the data is present in the cache memory, that the data that I want to write or data that I want to update is present in the cache memory. Now please consider this. Now the data that is present in the cache memory is a copy of the block of the main memory. Just think over it. The data that is present in a line of the cache memory is a copy of the data of the main memory. Now if I update the data in the cache memory, what happens is now there is a discrepancy between the value of the data in the main memory and the cache memory. So while performing the write operation, overcoming this discrepancy takes on a important stage. So we have to think about the discrepancy handling also. So how it is done is, if the data is in the cache, now there are again two possibilities. One, I can write the data to both the cache memory and main memory at the same time. That is called the write through policy. Write through policy means I am updating the data on the cache memory and the main memory both at the same time. Now this eliminates the possibility of any discrepancy between the data values between main memory and cache memory. But this has the disadvantage that now the operation will be performed at the access rate of the main memory. Why? Because I'm performing the operation on both cache memory and main memory. Even if I'm doing it simultaneously, the total time taken will be governed by the time taken to operate on the main memory. Say for example, the cache memory can be updated in 1 second and the main memory can be updated in 10 seconds. Even if I'm doing it simultaneously, the total time taken will be 10 seconds. The second possibility is the write back policy. Write back policy basically means that in this case we only update the cache memory. We do not update the main memory here. So this can be done at a high speed, at the speed of the cache memory access rate. But the disadvantage here is that now there is a discrepancy between the main memory and the cache memory. Now this discrepancy can be indicated by using a special bit in the cache memory which is called the dirty bit. Now this dirty bit indicates that if the dirty bit is 1, it means that this particular line that is present in the cache memory has been changed since it was brought from the main memory. But if the dirty bit is equal to 0, that means that the line has not yet been changed and it is same as the data that is present in the main memory. If the data is not present in the cache memory while performing a write operation, that means it is again a miss condition. Now once again, there are two possibilities. One is the write allocate possibility, which says bring the line into the cache and then update it. And the second possibility says that update the main memory only. It will not bring the data into the cache memory. It will simply go and update the main memory. So these are the various cache read and write policies. Now let's see them in a different way. This is the cache read operation. This is the scenario of a read hit. Read hit means that the data is available in the cache memory. So the CPU generates an address. The address pertains to the main memory. It is mapped to address of the cache memory. The data is found in the cache memory and the data is sent from the cache memory to the CPU. This is the address bus. This is the data bus. Address bus is used to carry the address from the CPU. Data bus is used to carry the data from the main memory or the cache memory to the CPU. This is once again the cache read operation, but here we are considering the possibility of the read miss. What it means is, here the data is not available in the cache memory and the CPU has to go and look for the data on the main memory. You can see over here that the address that is being generated by the CPU is going to the cache memory. The data is not found over here, so the address is sent to the main memory. Now from the main memory, the data is being transferred to the CPU, and at the same time the data is being transferred on the cache memory. So this is that scenario where simultaneously I am writing the data on the cache memory and the CPU both. So main memory is sending a particular piece of data to CPU and it is copying one block of data on the cache memory. If I talk about write operation, now once again there are two possibilities. One is the write hit and one is the write miss. So the address, if it is a write hit, that means the data is available in the cache memory. So the address is generated over here. The address goes to the cache memory. Now we are here considering the possibility that both the main memory and the cache memory are being updated at the same time. So you can see the address is being sent to the cache memory and the data is being sent to the cache memory, and simultaneously at the same time the address and data are also being sent to the main memory for the updation of the data in the cache and memory both at the same time. Here we are considering the possibility of a write miss. Write miss means here again we are exploring the possibility that it is a write miss and we are updating directly the main memory. You can see over here that the address that is being generated is being directly sent to the main memory, and the data that is to be updated or that is to be written is also being sent directly to the main memory. Right. Now this is a possibility, a write back cache. Write back cache basically means that we are updating only the cache memory and we are deferring the updation of the main memory. Now this is done if the data is present in the cache, that piece of data is updated and the value of the dirty bit is set to 1 to indicate that this particular line of data, since it has been brought from the main memory, has been changed by the CPU and it needs to be updated on the main memory. Now let me repeat it again. The dirty bit indicates whether this particular line of data has been changed or not since it was brought from the main memory. If the dirty bit is equal to 0, if the dirty bit is equal to 0, that means the value of the block in main memory and cache memory is still the same. There is no discrepancy. But please understand, once the entire operation of the program is completed, the cache will be emptied. It will be flushed. Or if the cache is full and the main memory wants to bring in one more block of data into the cache memory, any particular line will need to be replaced. What if there was data in the cache memory which was not yet updated on the main memory? So if I flush the memory or if I replace a particular line in the cache memory before updating it on the main memory, there will be a ambiguity in the value of the data. So the dirty bit eliminates this possibility. Now the dirty bit, if it is 1, indicates that the value present in this particular cache line and the main memory block are different. So before the cache memory is flushed or this particular cache line is replaced because of the application on sub replacement policy, if the dirty bit is 1, then this data is updated on the main memory before this particular line or the cache memory is removed. Let's take a simple example. The access time of a cache memory is 50 nanoseconds and that of main memory is 500 nanoseconds, right? It's simple. So we say that the cache memory access time, we have already talked about the performance issues. We have seen that the expression for effective time TE is equal to H multiplied by TC plus 1 minus H multiplied by TM, where TC is the cache memory access time and TM is the main memory access time. So a similar question, access time of a cache memory is 50 nanoseconds and that of main memory is 500 nanoseconds. It is estimated that 80% of the main memory requests are for read and the remaining are for write. Now here is a little twist. the memory is now being used for both read as well as write operations. The hit ratio for the read access is 0.9 and a write through policy is being used. So you have to determine the average access time considering only read cycles, and what is the average access time if write requests are also to be considered. Now what I want you to do is, I want you to pause this video here and try to solve the problem on your own first. You can very easily find out the average access time for the read operation. For the read operation, you just have to stake 50 nanosecond cache memory access time, 500 nanosecond main memory access time, and the hit ratio is 0.9. Right? You can solve for read memory over here. The point being, what do we do for the write operations? So pause the video here, try to solve it on your own. If not, then you may continue. Now, for the read operations, we can very easily find the average access time. It is simply 0.9 is the hit ratio, 50 is the cache memory access time, 500 is the main memory access time, and this is 1 minus h. So this comes out to be 95 nanoseconds. Now, the read request probability is 0.8. It is given over here. That means the probability of write request is 0.2. If 80% of operations are read, that means remaining 20% are for write. So the average time for read is 95 nanoseconds. Average time for write is 500 nanoseconds. Why? Because I'm using a write through policy where both main memory and cache memory are being updated simultaneously. Right? So the hit ratio for read access is 0.9, which we have already used for finding out the average time for this. Now T read is equal to 95 nanoseconds, T write is 500 nanoseconds. Now you can once again find out the weighted average of the two. 80% operations are read operation, 20% operations are write operations. So the entire access time considering both read and write comes out to be 176 nanoseconds. Now the various replacement policies which are used in case the cache lines are all full have been listed over here. The first is LRU, which stands for least recently used. If all the cache lines are full and you want to replace a particular cache line, some cache line, then you will use the one line which has not been used for the longest period of time. Now before I go any further, let me stop over here and tell you one important thing. Now after this topic, we will be talking about something called the cache mapping. Now when we talk about the cache mapping, you will see that there are three types of mappings. There is direct mapping, there is set associative mapping, and there is associative mapping. Now whether a particular replacement policy is required or not depends on the mapping. For example, in case of direct mapping, you do not require any replacement policy. Whereas in case of associative and set associative, you require replacement policies. Let's take a simple scenario that the cache lines are all full and you have the flexibility that you can put the main memory block into any cache memory line. Now, if the cache memory is all full, which is the cache line that you are going to replace? If we are using LRU, it means you will replace that particular line of the cache memory which has not been used for the maximum amount of time. LFU, least frequently used, this means replace that line of the cache memory which has been used the least number of times. Does not matter that whether it has been used most recently or least recently. If it has been used least number of times, it will be replaced. FIFO, it's quite simple, first in, first out. The cache line which was brought in first will be eliminated or will be replaced first. Next, random, just at random you can replace any line. Optimal is actually not a policy, but it is used for comparing the things. Optimal policy basically means that when I'm executing a particular operation, executing a particular application, we try to use the above four replacement policies and then we compare the results. We use LRU, LFU, FIFO and random, and then we compare the results to find out which one of the four is the optimal policy. So the optimal replacement policy is determined only after the program has been actually executed, and so it is of little help to a running program. This is just for the purpose of comparison. So these are the different replacement policies. Now mapping, it's quite an extensive topic, so I believe we'll discuss it in the next lecture. Okay, thank you.